break for Module 2. I hope that you were able to grasp the concepts in the previous module quite well because we're going to build upon them in Module 2. So Module 2 is going to be divided into 2 lessons. In the first lesson, we'll get a brief introduction to machine learning. I'll refer to that as ML from now on. And we'll get a glimpse of 3 types of algorithms, namely regression, classification, and clustering. Following that, in the second lesson, we'll be looking at Azure Machine Learning, which is a platform for machine learning on the cloud that helps accelerate and manage the ML project lifecycle. And we'll see a demo of the automated machine learning functions in Azure Machine Learning. I'll show you how you can get started on your machine learning journey on the Azure portal and train an ML model. Lesson 1 will serve as an introduction to machine learning, and I'll be talking about the 3 types of machine learning, namely regression, classification, and clustering. But of course, it is difficult to talk about machine learning and data without some basic math. But my goal is not to teach you linear algebra or any sophisticated algorithms. I just want to give you a little peek behind the curtain and gain an intuitive understanding of how machine learning works. And this understanding will help you to visualize the more advanced machine learning applications. And you don't have to worry, you will not be required to carry out any intensive calculations to be able to build and train your own ML models. This is where Azure Machine Learning comes to the rescue. We will talk about that in Lesson 2. Before we jump into a discussion about machine learning, let's take a second to think about traditional programming. The idea in a traditional programming model is that a programmer, a person, thinks about what this program has to do, and they have to provide the code or the instruction or an algorithm to teach the computer how to execute a task. And any input we provide is subsequently going to go through that algorithm designed by that programmer, and that output is going to come out. It's like going through a set of instructions. Machine learning, however, is the creation of a predictive model by finding relationships in data. So in this instance, we are providing data, which is both the input and the output to the computer, and letting the computer think for itself and come up with the algorithm. This algorithm, once again, is not done by the programmer. That is the machine learning model. So why do we need to do this? In our daily lives and work, you and I, we create a lot of data, massive amounts, in the form of things like social media. There's all these likes and comments, our text messages, the way we write emails, photos we take, images where we consume, sensor data in our homes, our thermostats, our air conditioners, our lights, all of these are creating data all the time. For example, and even when we drive, this list is never ending. There's so much data. And this data can be harnessed by data scientists to draw insight and train machine learning models. And that data sheds insight into how certain tasks can be automated. In essence, we use this data to train a machine learning model to power an AI-based software to carry out the jobs of the future. So machine learning is the foundation for most AI solutions. Let me walk you through an example of one such machine learning model. Imagine you're a botanist. So you go around collecting flowers and you study them. So when you used to collect 10, 20, maybe even 50 flowers a day, you could classify them manually. Based on the species, you could study them and you could classify them. But as time goes by, you start collecting more and more flowers. You're collecting 200, 500 flowers. And there's so much more work to do in terms of classification. So we want to try and automate this process using AI to classify the specimen in future. So we observe that we can examine and classify various characteristics of these flowers. So things like the length of these petals, the number of the petals, could be the size of the stem, the color of that flower. We call each of these things features. The features are characteristics of the flower. And the flower samples belonging to the same flower or the same family will have some common traits. That is their identity. Identity, and we refer to identities as labels. Label is a keyword I want you to understand. So all the specimen labeled Rosa multiflora are going to have some similarities. Proportionally, they're going to be somewhat similar. Likewise for the Bellis perennis and the Tulipa. This is the raw data that we feed to train our machine learning algorithm. The features in the form of colors and measurements, and the labels in the form of the name of the specimen. When we combine these together, the algorithm is going to understand the relationships between the features and the labels. And the result is a machine learning model that now has an intuitive understanding of these three species of flowers and can predict the species. And when I say predict, it is going to pick up a new flower that it hasn't seen before, and if you give it the characteristics of that flower, it is going to give you the label or the identity based on the features that are fed into it. And in this case, we obtain a new specimen, we feed in the features, such as the petal length, the number of petals, the color, and anything else that was used to train the model initially. And the model is going to provide you with a prediction on what it thinks the label of the flower should be. In summary, we're using past data of a human performing the task to teach a machine how to do the work in the future. This diagram provides a great overview of the types of machine learning that we will be looking at. There are two general approaches to machine learning. One is referred to as supervised, and the other is unsupervised. And the goal of both methods is to formulate a model or an equation that will be useful in trying to predict future labels as accurately as possible based on the features. Once again, labels is the name or the identity of that object. To have a good accuracy of outcomes for supervised machine learning, we need quality data with known label values that we can fit to a model. This can then be applied to new data for which we don't have the label values. Remember, labels are what we want to predict. This could be things like a house price, or identifying what image or what item is in an image, or whether someone is likely to default on a loan or not. So there are two types of supervised machine learning tasks. So first, I'm going to talk about regression. Regression is when you want to predict a numeric value. So this could be something like a price, a sales total, or some other measure. So let's take a second to help a fictional bike rental business, Hot Wheels Rental. Let's say Hot Wheels Rental is located at East Coast Park in Singapore, run by my dear friend, Mr. Steve Seagal. Mr. Seagal wants to be able to predict how many bikes are going to be rented on any given day so that he can be prepared in advance. Before we can start to train this model, we need some data from him. And Mr. Seagal, with his great foresight, has been keeping track of the average temperature every day. This temperature is our feature. And most importantly, he's also been keeping track of the number of bikes that were rented, and that is our label. So recall, features are the characteristics and labels are the outcome in this example. So to help Mr. Seagal, I need to create a machine learning model to predict how many bikes are going to be rented given that day's average temperature. As we feed the data of past rentals and the corresponding average temperature to our machine learning model, a relationship starts to emerge. And that is the machine learning model that we want to provide to Mr. Seagal to plan his business strategy. In this example, we used only one feature for training. That's very simplistic and might not truly give us a very accurate picture. Typically, you would find several parameters being provided as features, being used to generate a more robust machine learning model. Other real-world examples of regression could involve things like spam detection in email, or weather forecasting, or housing prices prediction based on location, number of rooms, number of toilets, etc. Next, we have classification. Classification is another type of supervised machine learning in which we are trying to categorize or classify something, so hence classification. Recall, in regression, we were trying to get a numerical value. In classification, we want to obtain a category. So let's now travel to the other side of the world to assist a fictional clinic in Costa Rica, run by another dear friend of mine, Dr. Eva. Dr. Eva wants to help spot patients who are at high risk for diabetes, to intervene early and so that we can help patients manage this disease before it gets too serious. And Dr. Eva has gathered data from more than 1,000 patients over decades and hopes that we can put this to good use. And this data consists of features like height, weight, blood pressure, and so on. We don't need to worry too much about the details. The ML model will take care of that. And most importantly, we also need to have the labels for these patients, which is a yes or a no, represented by a 1 or a 0 value, depending on whether that patient eventually developed diabetes or not, while being monitored by Dr. Eva. 1 means they have diabetes and 0 means they do not. Our algorithm is going to learn from these past data points and provide us with predictions in the form of a probability value between 0 and 1 when we input the details of new patients. And our data scientists who are building this model will then have to determine a cutoff threshold value. So for example, if our cutoff value, hypothetically, let's say is 0.5, and our algorithm gives us a value of 0.65, which is above our cutoff value, this will be considered a yes, or will be rounded off to a 1, and that person will be deemed at high risk for diabetes. Whereas a value of 0.4, which is below the cutoff, will be rounded off to a no or a 0 value. So of course, no algorithm can be perfect. It can only give us a probability value, and we need to tune our threshold value by working with the subject matter experts and plan the training of the machine learning model to improve our accuracy and the usefulness of the model. In some applications, such as when it concerns health and safety, we might want to be a bit more cautious. So it might be preferable to flag someone as high risk wrongly rather than potentially miss someone who is truly high risk. So the amount of error you're comfortable with will depend on the severity and costs associated with these errors. Other real-world examples could be classifying someone as high or low risk of missing a loan repayment, or deducing if a user login is legitimate or might be a hacker when someone is logging into an account. Finally, we have unsupervised machine learning. When we provide training data to an unsupervised machine learning model, there are no labels provided, just features. Recall, labels were things that we were considered answers. So this time we have no labels. So this approach trains a model to group similar items based purely on their characteristics. It is just going to look at their features and try to establish some sort of a similarity and put them together in groups or clusters. Clustering determines grouping based on how similar these data points are to each other, with no guidance from the scientist or the analyst that is carrying out this experiment. So imagine we have a table with data about 10,000 vehicles. We don't quite know how to start sorting them out. So we just throw this data into a clustering model and just indicate the number of clusters you'd like to see and let it do its magic. Only at the end of the clustering will you be able to determine what was the criteria that the algorithm picked up on. In this example, in these vehicles that were thrown into this clustering model, we see that these vehicles were separated largely based on their emission and fuel efficiency characteristics. Given a totally different data set or a different number of clusters, they might have been separated in a totally different manner. Perhaps by their production period or paint color, maybe even the dealership they were purchased from. We can only determine that after we see the real-world applications of clustering are incredibly powerful. You could carry out fraud detection on fraudulent insurance claims. We might be able to deduce crime hotspots based on certain activities or markers. It is also widely used in customer segmentation to discover segments that marketers couldn't possibly have imagined profiling, because clustering helps marketing professionals improve their customer base and segment customers based on things like purchase history, interest, or activity monitoring. And the clustering would help companies to target specific clusters of customers for specific campaigns. Please do understand the differences between these three types of machine learning models well, because it will be important for your understanding of AI moving forward and for the AI 900 exams. When we are trying to train a machine learning model, good data with well-defined features and labels is essential. And once we have that data, step one is to split the data into a training set and a validation set. And we often do a 70-30 or an 80-20 split. What does this mean? When you pick up a data set, since the data set represents events that have already happened, we know what the correct label is. So we set aside 20% of that initial data to be used as a test for our trained model. So we can see how close the predictions are to the actual values are of this 20%. And there are a variety of metrics for measuring the model performance, such as root mean square error, R2, or mean absolute error, amongst others. And using this training data set, we must determine what kind of algorithm to fit the training data to a model. Often there is a bit of trial and error here, and we can choose to run the same process with multiple algorithms to obtain the best result. Sometimes there isn't much exactness to it. We do a bit of trial and error. And then we train our model using just 80% of the data. This is the learning component of machine learning. We allow the computer to try and capture the relationship between the features and the labels in a model. Training is the action of iterating on an algorithm to best capture those relationships. And after completing the training in step 3, we have a model that has established a relationship between the features and labels that we can now test. Remember the 20% of data that we set aside? It is known as the test data. So if you see the diagram on the left, you see an arrow under the number 4, which indicates that this is from that initial data set that we have. This is the 20% that we didn't use for the purpose of training. We can now use it to test how closely our model's predicted labels are to actual labels. This serves to grade our model's performance. And in the case of unsupervised learning, where we don't know the actual labels, we measure how well our model's predicted labels were at separating clusters. And there are many types of evaluation metrics. The important thing to remember is that the goal of machine learning is to find a model that gets as close as possible to predicting the actual label. The best model can still have some margin of error. It is never going to be 100% perfect. Based on how comfortable we are with the evaluation metrics, we can make some tweaks and changes and repeat that process, restarting from step 1. And that is the end of lesson 1. Moving on to lesson 2. In this lesson, we'll be talking about Azure machine learning and what Azure machine learning is. We'll look at automated machine learning and get a brief introduction to the designer as well. But first, let's understand what is Azure machine learning. Azure makes it very simple for you to use and execute machine learning workloads on the cloud. But before you can do that, you will need an Azure subscription. A subscription can be thought of as a billing and access boundary that lets Azure know how you'll be paying for the services that you're deploying. And it also allows organizations to control and govern who is allowed to create, access, and delete resources on the Azure cloud. And inside the subscription, you will need to create an Azure machine learning workspace. We'll shortly see how that is done. A workspace can be thought of as a logical container for resources that you need to manage machine learning projects. And the first of these resources is compute. Compute is needed to run machine learning workloads on the cloud instead of in your local computer. Running large machine learning workloads on your computer could take days or even weeks at times based on how much data you have. On the cloud, you have almost unlimited processing power, and that helps bring down the amount of time required to train your machine learning models. Next, you'll need your data. Your data is vital to build machine learning solutions. Managing data means being able to handle large volumes of data, but more importantly, also allowing it to be easily accessed for the purpose of being used for training your machine learning models. And every time you have a hypothesis on how to build a certain model, you will need to run a job to test it out. In the past, data scientists might try different algorithms and approaches to solve problems in a variety of ways. And a couple of days later, they might realize something I did a couple of days ago accidentally gave me best results. I'm sure I wrote it down somewhere on a napkin. Now, where is that napkin? Azure Machine Learning tracks every job that you run so that you can easily keep track of the different conditions of each experiment. So you can go back in time to see what were the conditions that got you the best results instead of keeping track of napkins for your variables. And next we have models. Experiments are used to train models, which you will register and manage in your workspace. These models can then be hosted and published for your consumption directly from Azure. And when you're ready to use your models in your applications, you can publish them as services that can be accessed over the public internet. In a while, I'll jump onto the Azure portal to give you a quick tour of the key areas and functionality of Azure, and then talk more about the machine learning capabilities that you can deploy on the portal. Inside the Azure Machine Learning Studio, we have Azure Machine Learning Designer. The Machine Learning Designer is a visual tool that we can use to create an ML pipeline. What are pipelines? Like it suggests, when water goes into one end of a pipe, it comes out the other end after traveling through the entire path, whichever way the pipe goes. And in Azure Machine Learning, pipelines are multi-step workflows that can help you to prepare data, to train models, perform model management tasks, anything that you require for that process. The Designer tool in Azure Machine Learning Studio enables you to create and run pipelines by using a drag and drop easy visual interface like the one that you see on the image on the right. It allows you to connect modules that define the steps and the data flow for that pipeline. By building out pipelines, we automate future processing of any new data that is coming into that pipeline. On the right side of the screen, you can see an example of a training pipeline. Let me walk you through that process. This pipeline starts with a data set. And in this case, that data set contains patient data and information about whether they have diabetes or not. And before we carry out any training for machine learning, data is usually pre-processed to clean it up and make it more suitable for building a model. And in this case, the numeric features in the data, things like height, weight, diastolic blood pressure, and so on, are normalized. And normalization means to convert them all to be on the same scale, to prevent any one factor from being overly influential in deciding the label. And this is a common pre-processing step for numeric features. And the Designer includes a normalized data module to do it without having to require any coding or programming knowledge. Next, we see a split data module. Split data is used to randomly split the data set into training and test subsets. This is also another common step in supervised machine learning pipelines. It allows you to evaluate the model using data that it has not been exposed to. The training subset is then connected to a train module, which in this case will fit the data to a function that predicts a diagnosis of yes or no for whether someone has diabetes. This is a classification function with two possible classes. So an appropriate classification algorithm must be used to train the model. And in this case, we see that the two-class logistic regression model was used. Some of you may caught that the word regression appears in the algorithm, but rest assured, this is a classification method. After training, we add another module. This module is used to score the validation data. In other words, we use the trained model to predict labels from the features. So the test data that we initially set aside includes the actual label value. So when we try to make predictions on that, we can see how close we actually got to the actual value. So when we use the score module, we can compare these two values using the evaluate model module to calculate the metrics to help us determine if the model is performing well or not. For a classification model like this, these metrics include simple accuracy as well as a confusion matrix of true positives, false positives, or true negatives and false negatives, from which other more discerning metrics can be derived. The other tool inside the Azure Machine Learning Studio is automated machine learning, which is the easiest way to train a machine learning model for supervised machine learning, where the features and labels are both provided. So models like regression and classification. Automated machine learning provides users with an easy-to-use visual interface to carry out machine learning operations, requiring little to no coding knowledge. Normally, to carry out the same operations, data scientists and data analysts would need to tweak certain features, have a good grasp of sophisticated computing and statistics knowledge. With AutoML, the user just needs to provide the training data and select the required model type. And AutoML does the rest. The best way to see how powerful this tool really is to jump into the demo and try it out. And that's exactly what I'm going to do. And now let me take you through the process of creating an automated machine learning resource inside of Azure. For that, I'm going to search for that machine learning, Azure Machine Learning, and I can select this resource right there. And to create any resource, always just look on the top left over here. Right now, I don't have any workspaces to display. I'm going to create a new automated machine learning workspace using the existing subscription. I'm going to place this in the same resource group. For the workspace name, let's just call this AI 900 Virtual Training Demo. As long as you see a check mark, this name is accepted. And I'm going to create it in the US region, in the East US region. And when you're creating an Azure machine learning workspace, you're automatically going to be getting things like the storage account, the key vault, application insight. Because for machine learning to work, you do need a lot of, you do need the storage account because you need a place to store your data. Because without data, you can't train a machine learning model. And you're also going to get the key vault, which is going to help store your sensitive information. And you're going to get application insights which will store information about your deployed models. So these are things that are automatically created, so you don't have to worry about them. And they will all go into the same resource group. With those settings in place, I think we can go ahead and create this machine learning workspace. Let's review and create. And once you click review and create, it is going to validate if you are allowed to create this resource based on your subscription and your permissions. So mine, it says the validation passed. Let's go ahead and create this resource. Now our resource has been created. Let's go ahead and jump right into it. When I click go to resource, we are brought to this page, which is the Azure Machine Learning Workspace that we created. To use this resource, we need to click on Launch Studio. When we launch Studio, we are brought to a different section of this website, which is different from the Azure portal. So this is the Azure portal, and this is my Machine Learning Studio. And the Machine Learning Studio is where you're going to be controlling all of your machine learning assets. Things like your data sets, the jobs and experiments that you run, various components, the pipelines that you create, the models that you're ready to deploy, the endpoints that are being deployed. And right now, this is an empty Machine Learning Studio. So let's go ahead and create some resources. So to run any machine learning experiment, we do need compute. And that's what I'm going to create first. I'm going to go ahead and create a compute cluster. Let's create a new compute cluster. And I'm just going to place this in the East US again, like all my other resources. I'm going to have a dedicated virtual machine of a CPU type. I don't need that much processing power, so I don't need a GPU. And I'll select this DS11 because it's sufficient for my needs. And I'll click next. And for the compute name, I'm just going to call this AI 900 Virtual Training Compute. And I'm going to have a maximum of 2 nodes. So these are 2 compute nodes working at the same time. That's what I want. And I can go ahead and create that. So this will just take a short while to create. In the meantime, let me show you around the studio a little bit. Next, we need data. So for the machine learning experiment that we're going to run, we're going to be predicting bike rental data. So let me bring up that data real quick. This is how the data looks. So we have information about the day, month, year, where there's a shop that is renting out bikes. So this is the actual number of bikes that they rent out at different days of the year and the conditions that were present during those days. So they've collected all of this data and they hope to use this data to make some predictions in the future of how many bikes they would need to have on standby on different days based on different conditions and different temperature and humidity. So let's bring this data set into our machine learning studio and see how to run this experiment. So I'm going to create this data set from a web file. This is a publicly available file at this URL, aka.ms/bike-rentals. I'm going to name this bike rentals. And this is a tabular data, as we saw in the Excel file a little earlier. Let's just describe this as bicycle rental data. So we need to do a little bit more configuration before this data set can be accepted. So right now the portal is understanding this data, figuring out how it can be used. So it's checking with me if indeed it is a delimited file format. And it is, so basically the file looks a little bit like that. All of those values are separated by commas. They don't actually look like a table, but Excel is able to understand this data and display it as a table. So the encoding, I'm not going to change that. Column headers, and I'm not going to skip any rows. With that, I'm going to click next. And this is the schema. The schema is every column that you saw a little earlier, the day, the month, whether the type was correct. So all of them, it says integer, decimal dot, integer. So this seems fine. It has read the data quite accurately. And I can go ahead and click next. Once I confirm the details, I can create this data set. And it's going to be imported as an asset into my machine learning studio. So this is just going to take a while. Meantime, I'm going to create an automated machine learning experiment. So you can create an automated ML without writing a single line of code, and that's what I'm going to show you right now. So let's go ahead and create this new automated ML job. And this data asset has already been loaded. I'm going to choose this bike rental data and go next. And we need to do a little bit more configuration to set up this automated ML job. I'm going to call this MS Learn Bike Rental. And the target column is basically the answer that you're trying to find. This is what the model will be trained to predict. And in this case, we are trying to predict the number of bikes that are going to be rented based on any given condition. So this is the column we need to choose as our target. And the compute, I'm going to use the compute cluster that I just created. This is basically what is going to crunch our numbers and build this model for us. So this has already been created that we just saw a short while ago. I select it and click next. And this is a regression job. So because we are predicting continuous numeric values, since it's the number of bikes and it's not a classification job. So I'm going to choose this. I'm going to change the additional configuration settings. And for the primary metric, this is what is measuring how successful our model has been trained. So I'm going to choose the normalized root mean square error. We don't have to worry too much about the math because there are many different ways to measure this, but we're going to keep it simple. And you can use all the support models to try and train your model, but I'm not going to do that. I don't have all the time. So I'm going to uncheck this and just select random forest and light GBM for testing and training this model. That's it. And for exit criterion, to determine success, I'm either going to train this for half an hour or when our metric score goes below a certain number. So for this, I'm going to say 0.085 as my measure of success. So whichever is achieved first, my model will stop training. I'm going to click save and also check your featureization. Make sure this is enabled. And click next. And I'm not going to change any of these and I'm going to hit finish. And this is going to start creating a new automated ML job. And that's all there is to it. So right now we're going to start training our model and soon we'll be able to see how successful it is and deploy it and use it. Now that we see that our automated machine learning model has completed and it tells me why it stopped running. So it says that it ran for 10 minutes and it exited because it hit one of my exit criterion, which was it hit the metric score threshold of 0.085. So this model has been trained and ready to go. So let's take a look at some of the success metrics. So here under models, we can see the various metrics. So the metrics that we used was normalized root mean square, but there are many other metrics that you could use to determine the success of your model. We go ahead and close that. I'm also going to show you the other explanations. And under explanations, you can see the aggregate feature importance. So this is an explanation of which of the features that we saw earlier played the biggest role in determining the final answer of the rentals. So it seems that working day is the most important factor. So this means, it probably means that weekends or weekdays are one of the most important things to consider. And as we increase the number of features, we see that the other factors don't play as big a role in determining the final rental data, the numbers for the rental. We can see a little bit more of the metrics. So these are all of the metrics that we saw a little earlier. And now let's go ahead and deploy this model. So this model, let's deploy it so that we can consume it and use it for the purpose of prediction. So I'm going to deploy this to a web service. And I'm going to name it predict rentals. And the description, I'm going to say predict bicycle rentals. And I'm going to deploy it as a compute container instance type. And I'm going to enable authentication. I think we are ready to go ahead and deploy this. So this could take a while. Now our model has deployed, so we see that the deployment status has succeeded. Let's go ahead and try and use this. Go to the endpoints, and this is our model. Let's go in there and check it out. So we see that the deployment status is healthy, it has succeeded, and we see this is the REST endpoint. This is how we're going to be able to consume our resource. Let's try to give it a test. So the way to test this would be to input all of the other data except for the rentals data, because the rentals data is the answer, the prediction that we would like to get from the model. So typically how we would test it is we would store some of the original data aside, because we know what exactly happened during that scenario, and so we already know what the answer is. So when we test it, we'll see how close the test result is to what actually happened. So here I have some data that I'm going to pass into this input, and we're going to give it a test. And when you click test, it's going to give you this answer. And this is how we start to consume this. And as you start to build out applications and carry out, build out more complicated solutions, this is how you would start to consume your deployment. So you have the REST endpoint, you have your primary key. This information will go into your code, and you could consume this from your application. Let's jump back to our content and continue where we were. Using the auto ML functionality is really that simple. And what I want you to take away from this lab is that features and labels are vital in planning your data set for machine learning. Automated machine learning is a low-code solution for machine learning, and anybody can make use of their data in impactful ways and deploy prediction models with just a few clicks without knowing intensive statistics or algorithmic knowledge. And I also want you to note that automated machine learning does not involve a drag and drop interface like Designer. So there are two different solutions. Do recall that compute resources are needed to run machine learning model training. Without compute, you cannot train machine learning models. And recall that once a model is trained, it can be evaluated and then deployed for use as an endpoint. With that, we've come to the end of Module 2. In this module, we got introduced to the concept of machine learning. We heard about 3 types of machine learning. 2 of them were of the supervised kind, namely regression, whose output is a continuous numeric value, and classification, whose output is a category or class of some kind. And the last one was unsupervised machine learning, known as clustering, where you don't provide the labels and you allow the machine to cluster and separate out your data points. And then we discussed Azure Machine Learning and talked about Azure Machine Learning Designer before diving into the portal for a short tour, and we looked at how to deploy a machine learning model using the Azure Machine Learning Studio, where we train a bike rental prediction model. So let's all take a 10-minute break to let all of that content sink in and come back prepared to discuss some applications of machine learning and AI in the upcoming 2 modules. So please, step away from your computers and phones. I'll see you back here in 10 minutes.